Light taking different routes around the cluster arrives at staggered times. A single supernova can appear, fade, and reappear in a mirrored image years later. These delays are not accidents but signatures, timing marks that let mass distributions be weighed in units of seconds. Near horizons, the hourglass narrows to a throat. Close to a black hole, a distant observer sees infalling clocks slow toward a standstill, their signals dimming and redshifting into silence. At the photon sphere, light itself can orbit, balanced between escape and surrender. Time there is stretched so thin that minutes far away correspond to long, reluctant beats in the depth. The same contouring shapes, temperature and age. Background radiation cools as the universe expands, but passing through wells adds tiny anisotropies, integrated Sachs-Wolf traces, where gravity's evolving grip lends or takes energy from ancient light. In the web of large-scale structure, potential wells and hills modulate not only motion, but the bookkeeping of when events occur and how they are seen. Thus, time's texture is not uniform fabric, but relief map. Geometry sets the contours, matter sculpts the basins, and clocks read the terrain. From mountain observatories to satellite constellations, from galactic lenses to the brink of horizons, one story repeats in different keys. Matter warps the arena. The arena guides matter, and in the margins of every signal, a clock quietly tells the tale of gravity's hourglass. Time leaves fingerprints, matter keeps them. In wood grain and glacier glass, in coral bands and crater rims, the past settles into patterns that can be read long after the moment has gone. Records bind moments to matter, turning passing weather into rings, passing seasons into layers, and passing light into spectra. The world becomes an archive, each shelf built by physics and chemistry, each page written in structure and stain. Trees tally years with alternating bands of fast spring growth and dense latewood. Dry summers squeeze the rings thin, wet years widen them. A forest becomes a ledger of droughts and deluges, cross-dated across valleys to reconstruct centuries of climate. Far to the poles, snowfall compresses into annual sheets of ice. Trapped in those layers are bubbles of ancient air, tiny ampules of atmosphere that preserve bygone concentrations of carbon dioxide, methane, and volcanic ash. Drilled and lifted to daylight, an ice core whispers the cadence of ice ages and interglacials with the steadiness of a metronome buried in snow. Lakes keep time in varves, light and dark laminations laid down year by year as spring floods and winter calms alternate. On seafloors, sediments accumulate chemical traces of temperature and productivity, ratios of oxygen 18 to oxygen 16 in shells from long-dead plankton shift, with the warmth of the water in which they grew. In cooling lava, iron-bearing minerals align with Earth's magnetic field, freezing compass needles into stone. Bands on the ocean floor record reversals of the field like barcodes, a moving tape that dates the opening of basins and the drift of continents. The heavens keep ledgers of their own. Starlight is stamped with spectral lines, the fingerprints of elements. Their positions and shapes reveal temperature, pressure, rotation and motion along the line of sight. Pulsating stars keep precise rhythms. Clusters display color magnitude patterns that age like faces, allowing entire families of stars to be dated at a glance. White dwarfs, the embers of sun-like stars, cool in predictable arcs. A population of such embers forms a cooling sequence, a cosmic thermometer turned into a clock that times the histories of clusters and the disk of the Milky Way. Information is the art of arranging matter so that one pattern can stand for another. DNA encodes ancestry and adaptation in a 4-letter scripture wound into every cell nucleus. A single mutation, a duplication, or a shuffled segment becomes a note in the long song of descent, and comparative genomics turns those notes into timelines. Epigenetic marks, methyl groups, histone modifications, layer recent experience on older text, a penciled margin that can fade or persist across generations. In rock, isotope ratios tally radioactive decay. In the brain, changing synaptic strengths and new connections stabilize a moment into memory. Thermodynamics charges a fee for all of this bookkeeping. Writing a mark dissipates heat, erasing one costs energy. Landauer's principle quantifies the minimum toll. Removing one bit of information must release at least KTL and KT-2 of heat to the surroundings. Real devices pay more, but the logic is universal. Living systems meet the cost with metabolism. By consuming free energy and exporting entropy, cells maintain low entropy order. Proteins folded, gradients held, memories stabilized, within a high entropy environment. The brain spends a lavish share of the body's power budget to keep fragile patterns intact, refreshing them against molecular noise and decay. Memory is not magic. It is a physical state that resists forgetting long enough to be useful. In neurons, long-term potentiation strengthens synapses through cascades of biochemical change, altering receptor densities and local structure. New spines bud from dendrites. Networks replay patterns during sleep. Fleeting signals consolidate into durable traces. The price is paid in ATP, in blood flow, in careful ion pumping across membranes. Forgetting, too, has physics. Pruning connections and overwriting synaptic weights generate heat and molecular wear. Another reminder that even silence has a thermodynamic bill. On planetary scales, isotopes serve as timestamps. Zircon crystals shelter uranium and lead in lattices that shrug off disturbance, preserving clocks that tick across billions of years. The resulting dates sketch the emergence of continental crust and the presence of liquid water early in Earth's history. Coral skeletons are crete bands that capture sea surface temperatures and storm scars. Speleothems grow in caves, layer by layer, recording rainfall in their oxygen isotopes and trace elements. Each archive has biases and gaps, yet together they overlap and corroborate, like eyewitnesses whose stories interlock. In astrophysics, lensing delays and echoes create calendars written in light's travel time. A quasar, split into multiple images by a foreground galaxy, will flicker at different moments in each arc. Measuring those delays weighs the lensing mass and constrains the expansion rate. Supernovae caught in different lensed paths can reappear years apart, their second act predicted by geometry. Even the cosmic microwave background, nearly uniform, carries tiny anisotropies that archive acoustic waves from the primeval plasma, a fossilized sound field from an epoch before atoms. All these records point in the same temporal direction. Causes precede effects, not by decree, but by habit of accumulation. Ash follows fire, a ring follows a season, a spectral redshift follows a climb from gravity's well. Traces collect downstream of events because entropy rises. States with more microconfigurations outnumber the tidy ones that came before. Retrodiction, inferring past causes from present marks, works because the world writes to its media more readily than it unwrites them. The arrow of time becomes visible in this quiet accounting. It appears in the soot on a ceiling, in the widened tree ring after rain, in the cooled glow of a white dwarf, in the hydrogen line shifted by a galaxy's retreat. Each mark is local, partial, and perishable, yet across scales they add up to a biography. Matter remembers by being rearranged, and forgetting comes as diffusion, corrosion, and noise wear patterns down. Between the making and the erasing, a span opens where histories can be read and lives can be lived. Memory in matter is thus the interface between physics and narrative. From molecules to mountains to galaxies, durable patterns preserve the order of happenings. The universe does not keep a single archive. It keeps many, redundantly and imperfectly, each paying the thermodynamic cost of keeping time. In their accumulation, causality becomes legible, and the flow from earlier to later gains substance, not as a metaphysical current, but as an ever-thickening palimpsest of marks no wind can fully erase. Beneath the calm of planetary arcs and pendulum swings lies a finer tremor. At quantum scales, the world does not march. It shimmers. Outcomes are not etched in advance, but offered as amplitudes, complex numbers that add and cancel like ripples crossing on a pond. Where classical paths would choose a single route, quantum dynamics admits a chorus. In the path integral picture, every possible history contributes, their phases weaving interference that brightens some futures and dims others. Probability in this realm is not ignorance of hidden detail. It is born from the square of amplitude, the born rules quiet arithmetic. A slit opened or closed changes the pattern not by pushing particles around, but by rewriting which alternatives are allowed to interfere. The strangeness has precision. Statistical predictions survive relentless tests, from single photon interferometers to superconducting qubits looping through finely tuned circuits. Time enters the formalism as a parameter guiding smooth, unitary evolution. The Schrödinger equation carries states forward with reversible grace. Yet measurements arrive as discrete landings on definite outcomes, clicks in a detector, dots on a screen, an apparent jump not present in the continuous equation. The pace itself can shape result. Observed incessantly, an unstable system hesitates to decay, the quantum Zeno effect turning attention into a kind of stasis. Between smooth evolution and sharp outcomes lies the environment. No system is perfectly alone. Stray photons, phonons and fields brush against it, recording partial information. Decoherence spreads phase relations into the surroundings, suppressing interference between certain alternatives and selecting robust pointer states. What appears as collapse becomes, in open system language, the practical loss of coherence to countless unseen degrees of freedom. Facts once smeared turn crisp not by magic, but by entanglement with a world too large to reverse. Entanglement is the signature bond of this scale, stitching distant parts into single descriptions. Pairs prepared together can show correlations that violate Bell inequalities, a pattern impossible for any theory of pre-assigned local properties. Signals still respect light cones. No knob turned here can send a message there faster than light. The correlations are stronger than classical, yet disciplined, bounded by quantum rules and indifferent to schemes for superluminal talk. Open systems drift toward equilibrium under the gentle governance of master equations. In the Lindblad framework, coherence leaks at calculable rates. Temperatures and couplings set the timescales for forgetting. Out of these flows, an arrow of time emerges without decree. Decoherence and dilution convert crisp phase relations into heat. Records accumulate in the environment. Erasure has a thermodynamic cost. Microscopic laws remain largely time-symmetric, but typical states evolve toward the many over the few, entropy's preference written in Hilbert space. There are formalisms where time itself is relational rather than imposed. In the Page-Wooter's construction, a composite state can be timeless as a whole, while subsystems serve as clocks, their correlations defining before and after. In the thermal time hypothesis, a state determines its own notion of flow through a mathematical generator, tying tempo to information rather than to an external parameter. These approaches do not rewrite experiments. They suggest that temporal order may arise from correlations and boundary conditions, not from an absolute cosmic metronome. Bridges to the classical world span this terrain. The Ehrenfest theorem shows that quantum averages can follow Newton-like motion when states are narrow. UKB methods recover rays and trajectories where phases vary slowly. Decoherence prunes interference so that macroscopic objects trace stable paths. Continuity, so familiar at large scales, is composed from countless quantum intervals, much as a fluid smooth surface emerges from molecules in ceaseless motion. At the margins of current knowledge, Planck scales mark a frontier rather than a minimum tick. There, quantum theory and gravity both demand a say, and the grammar is still being drafted. Yet within tested domains, the rules hold with crystalline reliability. Indeterminacy is not chaos but syntax. Superposition, interference and entanglement are its parts of speech. From their interplay, classical stories are written, one definite outcome then another, while underneath, amplitudes continue their silent negotiations, composing continuity moment by moment. life carries a pocket of time, beating within cells and organs like quiet metronomes. In a world where daylight slides across the sky and temperature ebbs and flows, organisms carve out their own cadence, translating cycles of light and darkness into chemistry, electricity, and behavior. At the center of this orchestration lies a master pacemaker, a paired cluster of neurons in the hypothalamus called the suprachiasmatic nucleus. It keeps near 24-hour time through molecular feedback loops. Genes such as PER and CAR-Y rise and fall in expression, their proteins returning to inhibit their own production and hours later releasing the brake. This transcription-translation cycle creates a self-sustained oscillation. Around it, thousands of peripheral clocks in liver, heart, lung, skin, and even immune cells tick to their own versions of the same script, coordinated but not identical. Light sets the phase. Specialized retinal cells containing melanopsin, intrinsically photosensitive ganglion cells, send signals directly to the suprachiasmatic nucleus. Blue-rich photons near 480 nanometers are especially persuasive, shifting the clock earlier with morning exposure and delaying it with light late at night. The result is entrainment, an internal rhythm synchronized to the external day. When schedules or travel misalign the two, jet lag emerges, mood dulled, sleep fragmented, until light, darkness, and routine coax the oscillators back into harmony. Hormones carry the clock's instructions through the body. Melatonin rises in darkness, whispering that night has arrived, while cortisol peaks near waking, priming metabolism and alertness. Core body temperature drifts with the day, typically dipping by about a degree near dawn and rising toward evening. These waves are not decorations, they gate when food is best processed, when muscles perform, when memory consolidates, and when the immune system patrols most effectively. Beneath the daily cycle, other tempos interleave. The heart's sinoatrial node fires with its own pacemaking currents, an electrochemical rhythm steered by the autonomic nervous system and metabolic demand. Lungs breathe in ultradian patterns, neurons chatter in oscillations from slow delta to quick gamma, and endocrine systems trace longer arcs. Menstrual cycles, seasonal breeding, migration. Development itself is timed. Somat clocks tick during embryogenesis, carving vertebrae with remarkable regularity. Molecular gears keep the beat with exquisite resilience. Circadian oscillators show temperature compensation. Rates of the underlying biochemistry change with heat, yet the period stays near a day. This stability is not costless. Maintaining gradients, resetting ion channels, transcribing and degrading proteins all consume energy. Metabolism pays the fee so that ordered rhythms can persist within a disorderly environment, exporting entropy to keep the internal score. Feeding, fasting, and activity feed back on the clocks. A late meal can shift the liver's schedule independent of the brain, altering glucose handling and lipid metabolism. Exercise in the afternoon can nudge skeletal muscle clocks and improve sleep that night. Chronic misalignment, shift work, irregular meals, irregular light can push subsystems out of step, blunting hormonal peaks, disturbing appetite, and increasing risk for metabolic and cardiovascular disease. Perceived duration is a construction built atop these physiological tides. Under fear, time seems to dilate as attention sharpens and memory sampling densifies. During flow, minutes compress as prediction and action align. Dopamine modulates internal interval timing, stretching or shrinking subjective seconds, while aging broadens the ticks. Circadian amplitude diminishes. Chronotypes drift later in adolescence, then often advance in older adulthood. The sense of how long depends on arousal, novelty, and context, as much as on the clock on the wall. Sleep weaves the daily ledger into permanence. Slow waves sweep across cortex, spindles spark in thalamus, and synapses recalibrate. Memories stabilize as some connections strengthen and others soften. The glymphatic system pulses cerebrospinal fluid through perivascular channels more vigorously during deep sleep, clearing metabolic byproducts. These nightly housekeeping tasks unfold on a schedule set by both circadian timing and sleep pressure from wakefulness, with adenosine accumulating as hours pass and receding after rest. Even at fine scales, noise challenges precision. Thermal fluctuations jitter reaction rates. Stochastic gene expression threatens regularity. Biological clocks answer with network design, coupled oscillators, redundant loops, and delayed negative feedback that smooths randomness into reliable cycles. Populations of pacemaker neurons synchronize through synaptic and diffusible cues, turning many imperfect clocks into one robust signal. Technology now listens closely enough to map these rhythms in everyday life. Wearables estimate phases from temperature, heart rate variability, and activity. Dim, warm evening light protects melatonin. Bright morning light and regular meals anchor the day. In medicine, dosing aligns with chronopharmacology to match drug action to biological windows, improving efficacy and reducing side effects. In performance, training shifts toward the hours when muscles and lungs naturally crest. All of these tempos remain tethered to physics. A photon is a message. Its arrival resets molecular gears. Ion pumps move charges across membranes against gradients, spending ATP to preserve excitable cells. Heat diffuses, imposing noise, while the geometry of vessels and tissue shapes delays and flows. Biology stands as a small island of measured rhythm contoured by universal laws, translating sunrise and sunset into chemistry, translating chemistry into thought and behavior. Thus the body becomes a conservatory of time, where multiple instruments keep overlapping measures, some fast and bright, some slow and deep. The melody is not metronomic, it flexes with season and age, with food and motion, with light and darkness. Yet through the din of change, the composition holds. Life keeps time, and in keeping it, finds a way to endure, anticipate, repair, and remember. From shadows on stone and sand slipping through glass to cesium in sealed tubes, the measure of time has tightened from seasons to seconds to subtleties beyond intuition. Ancient gnomons watched the sun, water clocks bled minutes, pendulums brought regular sway. Quartz crystals hummed an electrical rhythm. Then atoms took the role of metronome, offering transitions that neither fatigue nor weather can sway. The modern second is defined by cesium-133. Exactly 9,192,631,770 oscillations of the hyperfine transition in its ground state. In atomic fountains, cesium atoms are cooled, tossed upward, and interrogated as they drift through microwave fields. Feedback locks the microwave to the atom's preference. The result is a tick, so even that if it drifted a second, the error would arrive after millions of years. Optical clocks climb to higher frequencies, trading microwaves for visible light. Strontium in optical lattices, ytterbium and aluminum in single-ion traps. Each references a narrow optical line stabilized by ultra-stable cavities. Frequency combs bridge optical ticks to radio counters, making the fast countable. Fractional uncertainties near 10 to the minus 18 turn height into time. A clock raised a centimeter runs measurably faster. No single device keeps civil time. Coordinated universal time is an ensemble average of hundreds of atomic clocks linked by satellite transfer and increasingly optical fiber. International Atomic Time, TAI, flows without leap seconds. UTC adds them to stay near Earth rotation, whose winds and tides refuse perfect regularity. Laboratories compare strontium to cesium, building a bridge toward redefining the second in optical light. Navigation depends on synchronized ticks. GPS, Galileo, GLONASS, and Beidou satellites broadcast stamped timestamps from orbits where gravity is weaker and motion is swift. Relativity is not a correction, but the operating principle. Altitude speeds the onboard clocks, velocity slows them, and both effects are pre-compensated, so receivers can trilaterate position to meters or better. A handful of nanoseconds becomes a map. Timekeeping has become geodesy. Portable optical clocks and fiber-linked comparisons sense gravitational potential. Lift a clock and it hurries. Lower it and it lingers. Networks of such instruments can contour the geoid, track groundwater changes, and monitor volcano inflation, reading Earth's shape in the pace of time. Chronometric surveying turns seconds into elevation. Clocks also interrogate nature's foundations. Long campaigns compare different atomic species to test whether constants, like the fine structure constant, drift. Sidereal modulations probe Lorentz symmetry. Synchronized arrays listen for transients that could betray passing dark matter fields. Proposals even imagine clock interferometers for low-frequency gravitational waves, using time itself as an antenna stretched across continents. Thus, the craft of time becomes a mirror. Each improvement reflects laws more sharply. Electromagnetism in spectral lines, quantum mechanics in line widths, relativity in rate shifts. The devices that tally days and guide ships to harbour now weigh mountains, test symmetries, and search the dark. In their quiet counting, the universe describes itself, one disciplined oscillation at a time. Light is the oldest archivist, crossing expanses with pockets full of dates. Every photon departs carrying a temperature, a colour, and a delay, and arrives as a stamped envelope from a particular place and hour of the universe. The first entries in that archive are faint and everywhere at once. The cosmic microwave background, a near-perfect glow laid down when the young cosmos became transparent. Its temperature is just 2.725 Kelvin, yet tiny ripples, only tens of microkelvin, sketch the scale of primordial sound waves in the hot plasma. Peaks and troughs in that pattern reveal the amounts of ordinary matter, dark matter, and radiation, while polarization swirls, add notes about rionization, and the way gravity has tugged on those photons since. A single sky becomes a ledger of contents, age, and geometry. As space expanded and cooled, later pages were written in starlight. Spectral lines act as barcodes, thin dark notches from hydrogen, oxygen, calcium, and more. Stretch those lines redward, and the cosmic scale factor is revealed. The farther the shift, the longer the journey, and the younger the universe when the light left. Hubble-Lemaitre expansion emerges from these displacements, and baryon acoustic oscillations leave a preferred spacing in galaxy surveys. The fossil ring of early universe sound now frozen into large-scale structure. Some sources carry clocks of their own. Type Ia supernovae brighten and fade in a characteristic way. Calibrate that curve nearby and it becomes a standard candle far away. Their combined story showed that expansion is not merely continuing, but accelerating, as if pushed by a pressure woven into space-time. Quasars split by gravitational lenses add another timing trick. Multiple images flicker with measurable delays, and those offsets weigh the lens and test cosmic distances with seconds as rulers. Between sources and eyes lies matter that edits the message. Intervening gas paints forests of absorption lines, with hydrogen's Lyman alpha series tracing the density and temperature of the intergalactic medium across epochs. Dust dims and reddens, its grain sizes encoded in the curve of extinction and in the subtle 2175 angstrom bump. Galaxy clusters imprint the Sunyaev-Zeldovich effect on the microwave background, slightly shifting photon energies as they pass through hot plasma, faint smudges that double as thermometers and signpost to mass. Closer to home, atmosphere turns stars into trembling points. Twinkle is turbulence made visible. Pockets of air with changing density bend wavefronts into moving speckles. Lift a telescope above the air, and steadiness returns. With it comes transit timing to the second. When a planet crosses its star, the dip in light reveals radius. The cadence and variations reveal additional companions. Spectra during transit whisper about atmospheres. Sodium, water vapor, hazes, etched as fine changes in color across the eclipse. Not all fossils are bright. Surface brightness dimming scales steeply with distance, making ancient galaxies appear ghostly even when intrinsically luminous. Yet long exposures gather their photons, building mosaics of the early universe where disks are clumpy, star formation is fierce, and mergers frequent. infrared views add the hidden half. Dust-enshrouded starbursts, glowing in wavelengths stretched beyond the visible, assembling heavy elements behind veils that only cool light can penetrate. Time itself is recorded in arrival. A solar flare's X-rays, a supernova's optical flash, a gamma ray burst's brief glare. Each is a dated telegram. Dispersion in plasma delays radio waves by frequency, turning fast radio bursts into probes of the electrons that fill intergalactic space. In lensed systems, the same event can replay years later in a mirrored arc, a cosmic echo predicted by geometry alone. Laboratories on Earth anchor this reading. Calibration lamps and frequency combs keep spectrographs honest. Atomic clocks timestamp photons to nanoseconds. Synchronized observatories catch the same transient from different longitudes. With these tools, light becomes both messenger and meter, cross-checked against standards, so that faint shifts translate into distances, masses, temperatures, and ages. Piece by piece, the timeline grows continuous. The microwave background fixes the first clear epoch. The Lyman alpha forest threads through the dark ages. Lionization lights the page with the first stars. Supernovae and lenses pace expansion. Galaxies and clusters trace